In the years 2023 and 2024, something very strange was going on, at least with regards to climate change. For the first time, we were at 1.5 degrees Celsius of warming, above pre-industrial times, for nearly 2 years. There were record sea temperatures. The world's forests, that normally absorb 3 or 4 billion tonnes of CO2 every year from the atmosphere, absorb virtually nothing. And now it seems the world's ice is melting much more quickly than anyone expected, and no one's really sure why. So in this video we're going to look at how climate change is affecting the world's ice masses, especially the Greenland ice sheet, because its melting now is exponentially increasing, and its central forecast for when it reaches tipping point, when it would start to melt exponentially, was at 1.5 degrees Celsius of warming. But then halfway through the video I'm going to say none of this matters, because there's another part of the world that's been affected by melting ice, and there the impacts of the melting ice are going to be much more devastating and happen much sooner than you might expect from what the ice sheets are doing. How devastating? Well, it's thought it will devastate the lives of 2,000 million people, 1/4 of the world's population. How soon? Oh, about the year 2100. So, first of all though, we need to become experts in ice sheets. There are 3 types of ice on planet Earth. There's permafrost, which is outside the scope of this video. There's sea ice. It just forms when the seas get to be cold enough, when they get to freezing point. It melts when the seas warm up. It only has a very small impact on climate change, in that it reflects a lot of the sun's heat energy back into space, but it doesn't affect sea levels. It doesn't have a tipping point, but we will cover it, but only very quickly. The main focus of the video will be on glacial ice, and glacial ice forms when snow falls in cold areas that are so cold that the snow survives until the next year when there's more snow. And over the hundreds of thousands of years, over the millions of years, the snow levels build up, the snow at the bottom gets compressed into ice. That's glacial ice. We normally think of glaciers as those slow-moving rivers of ice that go down the side of a mountain, but all ice, except for sea ice and permafrost, is glacial ice. So an ice cap on top of a mountain, an ice shelf where the ice has formed on land but has moved out over sea, an ice field, ice lying on level ground, an ice sheet. An ice sheet is absolutely massive. It has to be larger than 50,000 square kilometres. So there are only really 2 ice sheets in the world, the Greenland ice sheet and the Antarctic ice sheet. You could say the Antarctic ice sheet is really 2, the west and the east ice sheets, because climate change affects them differently. But at the moment there's only officially 2, Antarctic and Greenland. And I can explain what's going on with the Greenland ice sheet, and in fact all ice sheets, by looking at this diagram. The thing to understand about ice sheets is they can only gain mass through one way, through snow landing on the surface, but they can lose mass in one of 3 different ways. If it's warm enough during the summer, the surface will melt and some meltwater will run off. They can lose ice from their base where it grinds up against the land, but of all the ice they lose each year, most of it is lost at the edge. So the snow lands on the middle of the ice sheet. The ice sheet spreads out in the same way as a glacier running down a mountain will slowly make its way down. Ice sheets just spread out. When they get to their limits, they lose the ice, either because the ice melts or it breaks off. Ice sheets are very resilient because they're so huge, 50,000 square kilometres at a minimum. They're made of ice, which is very cold. The ice reflects 80 or 90% of all the sun's heat energy back into space. And if you remember from a previous video, water has a much higher heat capacity than land. So to increase the temperature of water, it takes 4 times as much heat energy as though you were trying to heat the same amount of land. It takes a lot of heat to warm up the ice, and even when the ice gets to be 0 degrees Celsius, the melting point of water, the freezing point of water, to take ice which is 0 degrees Celsius and turn it into water which is still 0 degrees Celsius takes so much heat energy that if you were to apply that same amount of energy to water, the same amount of water, the water would heat to 80 degrees Celsius. Well, water boils at 100 degrees Celsius, so it takes so much heat energy to convert ice to water, you could almost boil water with the same amount of energy. which makes the ice sheets very resilient. But they're surrounded by the seas and land. The seas bring warm water from the tropics. The land warms up more quickly. The smaller an ice sheet gets, the more vulnerable it is to goings on around the side. Here's a map that shows just how cold Greenland was. This is the average July temperature from 1968 to 1996. 1996 was an auspicious year for the Greenland ice sheet because since then, every year it's lost mass. But can you see how it just generates its own climate? It's a massive block of ice. It's just so cold. It makes it very resilient. And you can see in the diagram it says the average temperature in July for the Greenland ice sheet was between 0 degrees Celsius and -4 degrees Celsius. So even in the summer it was still very cold, still very stable. But these two charts are from 2024 and they show just how much warmer the Greenland ice sheet has become. On the 25th of September 2024, the Greenland ice sheet, or parts of it, were 15 degrees Celsius warmer than normal. So if it's normally -4, it was plus 10 degrees Celsius. And you can see for the average temperature between June and September, it was on average 1 or 2 degrees Celsius warmer. What's interesting is temperatures are rising due to climate change more or less in a straight line, in a linear fashion. So at the moment it's thought we're heading towards 3 degrees Celsius warming by the year 2100. And you can see it's sort of flat. But if you look at the rate of ice loss for the Greenland ice sheet, it's exponential. Each year it loses a bit more. So it started off 1996 is the last time it gained mass. So 1996 it was fairly level and it lost a bit more ice each year. Each year it loses a bit more ice. And it at the moment is going up much more steeply. Well, this is one of the symptoms of a tipping point. And a tipping point is where, for example, the Greenland ice sheet is gradually affected each year by climate change. By a little bit more, it melts a bit more, and eventually it gets to a state where the dynamics of the ice sheet's internal physics take over. And it's still affected by climate change, but its own structure collapsing has a much bigger effect on how much ice it contains than the normal gentle warming that it's been receiving each year. And the thing about tipping points is they're self-amplifying. So once the Greenland ice sheet gets to a stage where it's no longer large enough to have its own climate, where its structure is no longer stable enough to hold itself together, then it will just, it will melt much more quickly. The ice will be lost much more quickly. So what's happening on the Greenland ice sheet? Well, until 2017 at least, although it was losing 60% of its ice around the edges, which was normal for an ice sheet, the reason it was losing mass, the reason it was no longer stable, was because of the amount of ice it was losing from its surface due to meltwater. The Greenland ice sheet is losing more water than normal because of the increase of surface melting. 60% of its mass loss is through losing ice at the edges. 40% of the mass loss is from surface melt. But increases in surface melt are largely responsible for the increasing melting of Greenland. So that's 2017. But then in 2024, something very strange happened. The 2023 to 2024 year, as the year before, had strong melt rates throughout the northern hemisphere summer, but also above average snowfall during winter and in June. As a result, the balance between accumulated snow and melting ice on Greenland's surface ended above the 1981 to 2010 average. 2023 to 2024, the Greenland surface itself increased, which is quite unusual. Until then it had been losing mass because it had been losing ice from its surface. The increase in both melt and snowfall are exactly what scientists expect in a warming climate. But overall, Greenland has again lost more ice than it gained, even as in previous years Greenland was comparably cool compared to North America and Europe. And scientists expect more surface melt and more snow in a warming climate, because a warming climate is warmer, so it melts the ice more, but also a warming climate contains more water vapour, and when that water vapour falls in a cold area it turns to snow, so that's all expected. But the reason the Greenland ice sheet lost mass was because it was losing ice from the edges, and that was because high calving rates, the breaking off of icebergs. Icebergs are glacial ice. They start off on land even though they end up at sea. High calving rates, the breaking off of icebergs at the face of the ice sheet, meant that Greenland lost 80 billion tonnes of ice over the 12 months from September 2023 to August 2024. The last year to see a net gain in ice is still 1996. And here's a diagram that shows it gained ice in the middle and it lost ice around the edges. Remember, sea temperatures were at record levels during 2023 and 2024, so it's no surprising that ice calving at the sea is happening more quickly. But there's also something else going on to the Greenland ice sheet. Normally, an ice sheet will lose ice at the edges and gain mass at the centre where it receives the snow. Climate change caused that to change a bit. It caused the surface to melt. But now the structure of the Greenland ice sheet is no longer able to cope with the increase in temperatures. So, for example, when the ice melts on the surface, it leaves pools of water. Even if those pools of water remain until the next time it reaches freezing temperatures, so it doesn't lose the ice, but it's just water for some of the time, then water lying on the surface does not reflect so much of the sun's heat energy back into space. A warming, melting surface can support algae, where algae is green, or dark green. It does not reflect so much heat back into space. The Greenland ice sheet has its own glaciers, we'll call the glaciers that slide down valleys. They're either called alpine glaciers or mountain glaciers. So it has its own mountain or alpine glaciers making their way down. As they melt, they lose mass, which means they're lighter, which means they can speed up and flow to the seas much more quickly, or to the land edge where they will melt, because the land is warmer, because the land will heat up 4 times more quickly for the same amount of heat energy, 4 times more quickly than the ice will. The oceans are much warmer, so the glaciers arrive at the sea or the land sooner, and also the meltwater from the mountain glaciers is lubricating them. Also, the glaciers are coming downhill by the force of gravity. Normally there'd be snow and ice at the bottom of the ice sheet, which would be said to be buttressing the glaciers. It would be slowing them down or even stopping them. Once that ice and snow is melted at the sides, well, there's no more buttressing, and it allows the glacier to move down much more quickly into the land or to the sea. So to have a ice sheet disintegrate, you don't have to melt all the ice, but just the ice will spread itself out more quickly into the warm sea and the warm land, and it will melt there, not when it's still part of the ice sheet. Also, on the surface of the ice sheet, these things called moulins, these great shafts that go down into the surface of the ice sheet. But also, it's now realised there are lots of fissures. There are lots of sort of 2 centimetre wide sort of fractures in the ice sheet surface, and that allows warm air to go down into the surface of the ice sheet. They don't go that far, maybe only tens or hundreds of metres. I think the Greenland ice sheet is something like 3,000 metres tall, so they don't go down that far. But what's happening is the structure of the Greenland ice sheet is now being affected. It's just not melting more quickly, but the structure is being changed. It's being affected by global warming, and it's making it less resilient, which is why we've got these exponential increases in warming. This means, really, if it hasn't tipped already, I think it's only a matter of time. If it carries on, the rate of melting carries on this way, it's only a matter of time before it does. It's not just the Count Everything channel thinks 1.5 degrees Celsius of warming is where the Greenland ice sheet will reach its tipping point, but it's the official prediction from proper scientists. Some scientists say that the Greenland ice sheet has already passed its point of no return. The situation for the Antarctic is a bit different. The Antarctic is much larger than the Greenland ice sheet. If the Greenland ice sheet was to melt altogether, it would raise sea levels by about 7 metres all the way around the world. If the Antarctic ice sheet was to melt altogether, it would raise sea levels by 58 metres. It's absolutely enormous. If you look at this diagram, The East Antarctic ice sheet is still fairly stable, but the West Antarctic ice sheet is gradually getting to that stage where it's melting exponentially. But in the same way as the Greenland ice sheet, the West Antarctic ice sheet is losing ice around the edges. What's interesting about the Antarctic ice sheet is how old it is. It's now thought that there's been ice at the South Pole for at least 66 million years and possibly 100 million years. Well, that's the time of the dinosaurs, when temperatures were much warmer. 66 million years ago they were about 10 degrees Celsius warming, but 50 years ago the ice has survived this. Temperatures were 15 degrees warmer than they are now. The thing that's strange is that the Antarctic ice survived temperatures of 14 or 15 degrees Celsius higher than they are today, but in the official science, the forecast for when the East Antarctic ice sheet might collapse is less than 8 degrees Celsius. If anyone actually understands this stuff, please feel free to leave a comment and explain what the situation is. How's the Antarctic managed to survive such high temperatures in the past, 15 degrees Celsius higher than they are now? It's at the South Pole, it's very cold, it doesn't get much sun, and remember, water has a high heat capacity, has a high cost to melt ice from ice into liquid. So when people say we're at 1.5 degrees Celsius of warming for the Antarctic, well, this is hardly anything. The number one thing, though, everyone's very concerned about is sea ice at the Antarctic. There is ongoing research into the polar community to understand whether Antarctic sea ice is undergoing a regime shift. The past 2 years have been way outside anything we have witnessed in our satellite record for their winter months for Antarctic sea ice. Research suggests ocean warming has been important in pushing sea ice into this lower coverage state, and we also see preliminary indications of changed sea ice behaviour, suggesting that the underlying processes controlling the Antarctic sea ice coverage may have altered. There are Earth systems all the way around the world that have tipping points, and all Earth systems affect other Earth systems and are affected by other Earth systems. So we've got the record sea temperatures are affecting the Antarctic ice sheet and the Greenland ice sheet. And the Greenland ice sheet, by putting more water into the North Atlantic, is affecting the AMOC, the Atlantic Meridional Overturning Circulation Current. This current that brings warm water to the northern Europe and east coast of America. This is an example of where one Earth system is affecting another. In theory, it's possible there could be a global tipping point cascade where each Earth system sort of pushes the next one to its tipping point, and we see really fast changes. It's unlikely, but it's theoretically possible. Anyway, the oceans and the ice sheets are affecting each other. But as humans, we want to know, how is this all going to affect us? Well, I'm guessing one of the big ways is through the increase in sea level rise. Here's a diagram by the United Nations Intergovernmental Panel on Climate Change, Assessment Report number 6, Working Group number 1, and it shows how the Greenland and Antarctic ice sheets might affect sea level rises in the future. So, for example, they think in 2,000 years' time, if we have 3 degrees Celsius of warming, but at the moment we think we're going to have 3 degrees Celsius warming by the year 2100. So let's imagine that we manage somehow to stabilise temperatures at that rate. They say if we have 3 degrees Celsius warming, then in 2,000 years' time, the Greenland ice sheet will have caused sea levels to rise by between 60 centimetres, 0.6 of a metre, and possibly about 2 metres. Well, you might have heard, if the Greenland ice sheet goes past its tipping point, which it looks it may well have done or may well do soon, then within 1,000 years it will have melted completely. But this is saying in 1,000 years' time it will only have contributed between 0.6 and 2 metres, whereas we all know if the Greenland ice sheet melts completely, sea levels would rise by 7 metres. And of the 3 climate models that they use to try and understand how the Greenland ice sheet melting might affect sea levels, one of them thinks it will have melted completely in 10,000 years' time. But 2 of them think even in 10,000 years, sea levels will have only risen by something like 1.5 to about 5 metres, 6 metres. And for the Antarctic ice sheet, 3 degrees of warming by 2,000 years' time would be maybe up to 10 metres lost out of a possible 58 metres if it melted altogether. And in 10,000 years' time, the Antarctic might have melted to such an extent, according to the climate models that they used, it could have melted anywhere between about 1 and 20 or 30 metres if we have 3 degrees Celsius of warming still in 10,000 years' time. Well, this is an interesting thing, because the Antarctic ice sheet has survived much hotter temperatures in the past. But the Greenland ice sheet, if it has reached its tipping point, you would think, well, it'll have melted completely by then. This all seems very conservative, but don't worry, the scientists themselves don't believe this, and in the United Nations report they list all the ways the models don't accurately predict the future. They list all the things that the models don't take into account. And so because of that, instead of saying the official for 3 degrees Celsius of warming by the year 2100, instead of saying the official 0.61 of a metre, they say it's more likely to be 1 metre. In light of such deep uncertainty, we employ a storyline approach. So the United Nations uses storylines for situations where there's high levels of uncertainty. Even if there's a low probability of something happening, if it has a high impact, then they want to try and understand what it might be like. In light of such deep uncertainty, we employ a storyline approach in examining the potential for and early warning signals of a high-end sea level scenario unfolding within this century. In doing so, we note that the main uncertainty related to high-end sea level rise is when rather than if it arises. The upper limit of 1.01 metres of likely sea level range by 2100 for the shared socio-economic pathway 5-8.5 scenario. So that's a very high rate of melting. Well, shared socio-economic pathway 5-8.5, it has by the year 2100 nearly 5 degrees Celsius of warming. You might wonder, are we really heading for 5 degrees Celsius of warming by the year 2100? Sounds a bit high. But remember, the science so far has always underestimated the impacts of climate change for a certain amount of warming. So they're saying officially we're going for 3 degrees Celsius warming, but maybe it's worth imagining we're going for 5 degrees Celsius of warming. Even though we'll still get to 3, the impacts will be as though what we think they are or would have been for 5, because they always underestimate the impacts. But it is uncertain how quickly the long-term committed sea level will be reached. Hence, global mean sea level might rise well above the likely range before 2100, which is reflected by assessments of ice sheet contributions based on structural expert judgment, leading to a 95th percentile projected future sea level rise, though there's a 5% chance of the sea levels rising by 2.3 metres by the year 2100. A plausible storyline for such high-end sea level rise in 2100 assumes a strong warming scenario. Remember, all these documents were written before we got to 1.5 degrees Celsius of warming. So, and you remember, the United Nations is always encouraging people to keep 1.5 degrees Celsius of warming in touch. We've sort of gone past that now, haven't we? Even though we haven't maybe officially gone past 1.5 degrees Celsius warming. The official date is 2028 is the most likely date, so it's only 3 years away now. The storyline considers faster than projected disintegration of marine ice shelves and the abrupt, a sign of a tipping point, abrupt, widespread onset of marine cliff instability and marine ice sheet instability in Antarctica. Well, they're seeing that now, aren't they, in Antarctica? And faster than projected changes in both the surface mass balance and dynamical ice loss in Greenland. Dynamical ice loss, the ice loss that comes from the structure of Greenland's ice sheet breaking down, and not just the direct impacts of warmth melting ice. In fairness to the scientists at the United Nations, they have seemed to just disregard their climate models and come up with a more sensible prediction of how the ice sheets will be affected that I think most scientists would agree with. At sustained warming levels between 3 and 5 degrees Celsius, near complete loss of the Greenland ice sheet and complete loss of the West Antarctic ice sheet is projected to occur irreversibly over multiple millennia, with substantial parts or all of Wilkes subglacial basin in East Antarctica lost over multiple millennia, early warning signals of accelerated sea level rise from Antarctica could possibly be observed within the next few decades. This sounds all very dramatic. We haven't got to the point where I say it's not important. This all sounds very dramatic, but if you think to yourself, well, we're heading for 1 metre of sea level rise by the year 2100 possibly, we don't need to worry. I think Donald Trump said something like this recently, that the amount of sea level rise is so small we don't need to worry about it. What we're talking about is mean sea level. In practice with climate change, it's much more important to take into account extreme sea levels that come from storm surges and tides and the increase in meltwater from climate change. But in practice, sea level rises and the impacts of sea level rises will come much more from the general impacts of climate change and much sooner. So for example, I think sea levels have already risen since 1850 about 1/4 of a metre, and maybe they'll increase another 3/4 of a metre in the next 75 years. But already storm surges are about 2, or in some cases are 2.7 metres higher than they have been before. That's what happened in Storm Sandy in the United States. If we have 1 metre sea level rise by 2100, then combine that with the impacts of storm surges, then in China they will be really at risk, because 40% of China's population lives along coastal areas that is at risk from storm surges of 2.5 metres. Storm surges along the southern Chinese and northern and southern Vietnamese coastlines increase by up to 1 metre, significantly larger than expected changes in mean sea level rise over the same period. The length of coastline that is presently exposed to storm surge levels of 2.5 metres or greater will more than double by 2050. About 45% of China's population of around 1.4 billion and more than half of the country's economic output comes from coastal regions. The Chinese coast is home to important metropolises, including Shanghai, the country's most developed and richest city, as well as the port city of Tianjin and tech hub of Shenzhen. It's not just a future thing, it's already having impacts in China. Over the past 4 decades, rising sea levels along the Chinese coast have caused long-term effects, including erosion of coastal ecosystems and the loss of tidal flats. In 2022, high sea levels along the Chinese coast aggravated the impact of storms, dealing a severe blow to the provinces of Guangdong, Shenzhen and Shandong. The rise also contributed to heavy coastal flooding in Shenzhen and Hainan province, causing great economic loss. This is what Sir David King found out when, in the run-up to the Paris 2015 agreement, he spent a year researching this with Chinese and Indian scientists, and they realised that most of Chinese rice production are in these vulnerable coastal areas. Greenland going past its tipping point is such a long-term problem. It seems so insignificant compared to the much more immediate problems, not just from rising sea levels, but also from melting ice from other parts of the world. So for example, so far half of all the sea level rise has come from just the oceans being warmer and expanding. 20% has come from melting water from the ice sheets from Greenland and Antarctica. But 22% of the sea level increase has come from melting of mountain glaciers. Now we come to the most interesting part of the video, that the glaciers in the Himalayas are melting so fast that they will have a devastating effect from the meltwater. But more importantly, when they've melted, maybe by the year 2100, only 20% of them will be left. Suddenly 2 billion people living in that part of the world will suffer great hardship due to lack of water. The International Centre for Integrated Mountain Development finds that 70 to 80% of the current glacier volume in this region will disappear by 2100 under high emission scenarios. Remember, at one time all these documents I'm reading from were written at a time when we thought we can keep 1.5 degrees Celsius of warming within touch. So when anyone says a high emission scenario, they're thinking of somewhere between 3 and 8 degrees Celsius of warming, I'm guessing. Well, we're heading for 3 degrees Celsius of warming by 2100, so this is a real possibility now. Snowmelt provides fresh water for major rivers such as the Amu-Darya, supporting up to 79% of its flow, the Indus 40% and Helmand 77%. Over 120 million farmers in the Indus, Ganges and Brahmaputra basins depend on this snowmelt for their livelihood. You think to yourself, why haven't we heard about this, but we've heard about the Greenland ice sheet? Because in this part of the world, it affects countries such as Afghanistan, Bangladesh, Bhutan, China, India, Myanmar, Nepal and Pakistan. These countries don't have a great representation when it comes to writing the climate reports. If the greenhouse gas emissions continue to be produced at the rate they are, the Himalayan glaciers could lose up to 80% of their ice by 2100. This would be extremely detrimental, as the Himalayan glacier serves as the largest source of fresh water outside of polar regions and vital for 2 billion people who live downstream of the Himalayan mountains. The Himalayan glacier serves as a base point for multiple of Asia's rivers, all of which are responsible providing nearly 2 billion people with drinking water and irrigation systems used for farming. But it's not just a case of by 2100 suddenly there'll be no drinking water or not enough water for farming. That part of the world is completely being changed by the melting of its mountain glaciers. The State of India's Environment 2024 report has unveiled that the region has borne the brunt of 44% of India's natural disasters from 2013 to 2022, increasing severity and frequency of floods, landslides and thunderstorms, particularly in the Himalayan states, signalling an environmental crisis on the brink. Disasters occur more frequently and are getting more severe, causing a significant loss of life and damage to property. The emergence of new glacial lakes triggered by cloudbursts exacerbates the risks, leading to flooding whenever these lakes overflow. Climate change has also triggered shifts in the vegetation line in the Himalayas, with a notable migration of 11 to 54 metres per decade. Do you remember in 2022 the Indus River Valley in Pakistan suffered a great flood? 33 million people were affected, 1 million homes were destroyed, over 1,000 people drowned through the flooding. That was back in 2022. This was quite shocking. Since then, 500 people have drowned in Spain due to flooding. 1,000 people died on the Hajj in Saudi Arabia due to heat extremes. So these sorts of large deaths are becoming more normal. But back in the old days, in 2022, this was a really shocking event and happened a mixture of monsoons, heavy rain, and the overflowing of the glacial lakes, which are forming because all this water from the glaciers is melting and is building up, ready to cause troubles. In one of my early videos, 2 years ago, the Indus River Valley was one of the few parts of the world that had seen a wet bulb temperature of over 35 degrees Celsius. And at that temperature, humans have a very limited life expectancy. He may be only a couple of hours because, it's just too hot for them to cope with. So the Indus River Valley seems to be ground zero for climate change, or at least climate collapse. That part of the world doesn't just rely on water from glaciers, but they also have rainwater, obviously, and they have monsoons. But 2,000 million people, it's a lot of people. At the moment, they rely on this meltwater from the glaciers. By 2100, 80% of that will have gone. So it will be interesting to see how it turns out. It's already having a devastating effect, just the amount of water that's coming down from the melting. So that's the end of the video, really. What we learned? That the Greenland ice sheet may very well have gone past its tipping point, but because it's a slow tipping point, no one's really seemed to have noticed, and it probably wouldn't make that much of a problem in the near future. Much more serious are the storm surges in terms of sea level rise that are already affecting parts of America and China. But even more important than that, 2,000 million people could soon have their lives devastated, partly by too much water as the glaciers in the Himalayas melt, and then not enough water when they've gone altogether. So, thank you for watching. I'm going to put more references in the video this time. I had some questions from the previous video, and if I haven't put them in the video, if you see something there and you think, oh, I've missed something out, have a look in the video description. I'm going to put the references in there, and then if I get comments questioning it, then I'll add the comments, I'll add the documents in that people are interested in, so you can all see where I get this from. So anyway, thank you for watching, and I'll see you next time.